All right. Hi, everybody. Class D. We're going to cover a few things. It's going to be mostly review, actually, but we're going to cover the Pythagorean theorem. And what else? We're going to review some line stuff. And we're actually going to talk about, like, what is a line really? I know we've talked a lot about lines, but we maybe could talk about how to define a line. So this should be pretty brief. I'm hoping to keep it under 20 minutes. We'll see if I can accomplish that. So first of all, the Pythagorean theorem. The Pythagorean theorem is something you may have heard of already. It's perfectly fine if you haven't. I should label my pages, page 1. The Pythagorean theorem says the following. If you have a right triangle, so some right triangle like this, where that angle is 90 degrees, and these other two angles are less than 90 degrees and add up to 90 degrees. We have a right triangle, and we label the sides like A, B, and C, where A and B are the lengths of the legs, or the shorter sides, and C is the length of the hypotenuse, or the longer side. The hypotenuse is always opposite the 90-degree angle. The Pythagorean theorem says the following. Pythagorean theorem states that A squared plus B squared is equal to C squared. Or if you take the two shorter sides, square them, add them together, it's equal to the square of the longer side. Probably the most famous example of this, as you may already know, is this triangle. This is what we often call the 3, 4, 5 triangle. Because it is certainly true that 3 squared plus 4 squared is equal to, let's see, 9 plus 16, which is equal to 25, which is equal to 5 squared. That checks out. There are other nice integer values like this. Those are called Pythagorean triples. The next kind of most well-known one is the 5, 12, 13 right triangle, where we have 5 squared plus 12 squared. That's 25 plus 144, which is 169, which is equal to 13 squared. So this Pythagorean triple, 5, 12, 13, is also the sides of a right triangle. And satisfies the Pythagorean theorem. Any triangle satisfies the Pythagorean theorem. Not all of the sides have to have integer values. A couple more examples. Oh, not that. That's not an example. So did I label that page? I did. Cool. Let me label the next one. So another example would be, for example, this triangle. The triangle 4, 5, square root of 41. It checks out. Oh, this is a right angle. 4 squared plus 5 squared is equal to 16 plus 25, which is equal to 41, which is definitely equal to the square root of 41 squared. So certainly these sides make up the sides of a right triangle. It's not as nice. Square root of 41, I don't know what that number is, but I do know that the square root of 41 is bigger than the square root of 36, which is 6, and smaller than the square root of 49, which is 7. So the square root of 41 is some irrational number between 6 and 7. What we often like to do with the Pythagorean theorem is use it to find the unknown side of a triangle. So for example, if I said we have a triangle whose side lengths are 6, 5, and unknown hypotenuse, and I said, well, let's find the length of that hypotenuse. Let's call it C for now. So I want to find C. I'm going to set my equation. I'm going to say C squared equals 5 squared plus 6 squared. Right? The two shorter sides squared and add together equals the length of the longer side squared. Now we have to be careful here. We can't just square root everything. We cannot say that C is equal to 5 plus 6, right? C is not equal to 11. Just like over here, this hypotenuse side wasn't equal to 4 plus 5, right? 4 plus 5 is 9, and the length of this side is definitely less than 9. It's less than 7 even. So here's some idea. We're going to say that C squared is equal to 25 plus 36. C squared is equal to 25 plus 36 is 61. So C is going to be the square root of 61. We don't need a plus or minus here. right? Even though technically the negative square root of 61 is the solution here, because C is supposed to represent a length of a triangle, and a length should always be a positive value. So that would be the length of the missing side. Let's do a couple more. It doesn't matter how the triangle is drawn, right? I could draw, let's see, page, what do you want, page 4? Yeah, page 4. I could draw a triangle that was oriented very differently, say like this. Well, it's a big, I didn't mean to draw my triangle quite so big. Sometimes that happens though. Here's my triangle, and I'm going to label this side, I don't know, 8, and this side 5. And here's my right angle here. Now I want to find this side over here. I usually call the hypotenuse side C. I don't know why. It's kind of, I mean, because really it's like A squared plus B squared equals C squared. So let's call this unknown side that I want to know. Let's call it A. So whenever you're trying to find an unknown side, it's usually a good idea to label it. I'm calling it A because that feels normal. You could call it X or Y or whatever letter you like, or some other, like you could call it a Greek letter. So my equation here, remember the longest side, the hypotenuse side that's opposite the 90-degree angle, is always the one that's going to be squared by itself. So my equation here might look like A squared plus 5 squared equals 8 squared. Or if you prefer, you could totally write it in the other order. 8 squared equals A squared plus 5 squared. It doesn't matter which way you write it. I'm going to use this one just because, I don't know, the A squared is already on the left. So now I'm going to have A squared equal to 8 squared minus 5 squared, right? I'm just subtracting 5 squared from both sides. So A squared equals 64 minus 25. So A squared equals 64 minus 25 is what? 39. So A is equal to the square root of 39. Excuse me. Let's do one more. So let's say I've got this smaller triangle. Let's make it also interesting. Let's say it's like this. Can I actually draw it well? Maybe. There we go. Here's my right angle right there. And let's say we know this smaller side, let's call it, I don't know, let's make it like, sure. Try and come up with something special. Let's say this is 5, this is 7, and this is, we don't know. But I'm going to call it C. I use a question mark here. Let's call it question mark. So I'm going to say that, so smaller side, bigger side. So to solve this, I'm going to write 5 squared plus question mark squared equals 7 squared. So 25 plus question mark squared equals 49. Subtract 25 from both sides. I end up getting question mark squared equals 49 minus 25 is 24. So then my unknown side has a length of the square root of 24. We could leave it like that. I'm generally a fan of simplifying my square roots. So the difference between this answer and the previous ones is 24 is a number that has a factor that is a square number. So 24 is equal to 4 times 6. And the square root of 4 times 6 is the same as the square root of 4 times the square root of 6. But the square root of 4 is 2, because 2 times 2 is 4. So we really get 2 times the square root of 6. And that's considered a more simplified way of writing your answer. This would still be okay, but this is considered better. Kind of like how writing your answer as 6 over 2 is okay, but 3 is the more simplified answer. Or -5 over -2 is okay, but really +5/2 is what we should write. That's really all I have to say about the Pythagorean theorem. I do want to take a few more minutes to just talk about a few things about lines. The first thing really actually is, what is a line? And actually, I think I'm going to use Desmos for this. So I'll grab Desmos in a second here, but let's just say, look at the line. Let's look at the line. Was this the right number? Let's double check. It is. Here's the problem: is I start numbering. Right, this is page 4, and then I start numbering this problem 5. That's silly. Sorry, this is like an example. This is an example. I got to be better about that. So now page 5. All right. So I want to graph the line y equals 2x minus 3. And I'll graph it. It's not too terrible, right? I would plot my usual points. I would find my y-intercept. I would set x equal to 0. And I would substitute in 0 for x. I'm going to take my equation, y equal to 2x minus 3, and actually plug in 0 for x. So I get y equal to 2 times 0 minus 3, which is y equal to 0 minus 3. and 0 minus 3 is -3. So my coordinate for the y-intercept is going to be x is 0, y is -3. Similarly, for the x-intercept, I'm going to set y equal to 0 because my x-intercept should be on the x-axis, just like my y-intercept should be on the y-axis. To be on the y-axis, you have to have an x-coordinate of 0. To be on the x-axis, you have to have a y-coordinate of 0. So I set y equal to 0. I'm going to get, instead of having y equal to 2x minus 3, I'm going to have 0 equal to 2x minus 3. Solving for x, I have, so if I'm being very specific here, if I add 3 to both sides, then I'm going to have 3 equal to 2x. And then you can either divide both sides by 2 or multiply both sides by 1/2 to get rid of this multiplication here. So we do 1/2 times 3 equal to 1/2 times 2x. 1/2 times 3 is 3/2, or 1.5 if you prefer. And 1/2 times 2 is 1, so I get 1x, which is just x. So x is 3/2. I didn't really need to box that. So my point is going to be, sorry, my intercept is going to be x is 3/2, y is 0. Now, I'm going to plot some other points too, just because I want to. I mean, I'm going to graph the lines in a second here, but I'm going to plot another point just by picking other values of x. So for example, if I had let x equal 1, I'm going to get y equal to 2 times 1 minus 3, which is 2 minus 3, which is -1. So I get the point 1, -1 is also a point right there. And so now I'm going to draw my line. I'm using my handy dandy ruler here. And there's my line with arrows at the end like that. Here's what I want to say about lines. They're not too terrible to graph by finding the intercepts, or really any 2 points, but usually if someone asks you to graph a line, they're going to want you to tell them what the intercepts are. So if you already have to find these points anyways, you might as well draw the line through those 2 points. But additionally, we could find any other point on this line. So for example, what if I asked you to find a point on this line? Like pick any value of x. Well, let's say I picked x equal to 3. 3 is not my favorite. Let's say I picked x equal to 4. If x equals 4, y is going to equal 2 times 4 minus 3. Y is going to equal 8 minus 3, which is 5. So the point 4, 5, which I probably didn't plot on here very well, right? This point up here, 4, 5, would also be on the line if I kept drawing it further and further and further. Let's move over to Desmos for a second. So grabbing Desmos over here and resharing my screen. Oops, can I grab Desmos? Maybe. So let me do a new share. Let me share Desmos with you. That's not it. There we go. That's it. Am I there we go. Yes. So Desmos is a great tool. I encourage you all to familiarize yourselves with it. So let me just point out y equals 2x minus 3. Pretty straightforward line. And you can even click on it to see what the intercepts are, right? If I click, oops, did I do the right one? Yeah, 2x minus 3. Oh yeah, sorry, my scale just looks weird here because they don't show me all the, yeah. So there's my x-intercept, 1.5 or 3/2, 0. There's my y-intercept, 0, -3. Now, how many points are on this line? Well, let's find some. Like 1, -1. That's a point. I don't need to label it. Or let's see, 4, what did I say, 4, 5? Right. I could keep going literally forever. I mean, except I would die. But right, there's not an end to the number of points on this line. I could say, you know, if I set x equal to 6, 2 times 6 is 12, 12 minus 3 is 9. So the point 6, 9, can't see it, but if I zoom out a little bit, oh yeah, 6, 9 is on the line. What if I picked something like, what if I made a mistake? Like I said, x is 5 and 10 minus 3 is 6, which is wrong. If I do that, if x is 5, then I would say, well, 5, 10 minus 3 isn't 6, but I'll pretend like it is. Oh, look, point's not on the line, because to be on the line, the point has to satisfy the equation of the line. So when I plug in 5 for x, I should get not 6 because it's not on the point. I should get, let's see, 5 times 2 is 10, 10 minus 3 is 7. And that point is on the line. So what I really, really, really want to emphasize here is that a line is a collection of an infinite number of points. And all of those points satisfy the given equation, y equals 2x minus 3. You can even pick kind of weird points, like, say, not integer values, like x could be 1/3, and 2 times 1/3 is 2/3, and 2/3 minus 3, you know what? I don't even have to figure it out. I know it's negative 7/3, but I could write 2/3 minus 3. And there's the point. See, where is the point? It's the red one here, right there. So it's 1/3, 0.333 forever, and 2/3 minus 3, which is negative 2 1/3, or negative 8/3, which is negative 2.33, or sorry, negative 7/3, apologies, negative 2.3 forever. You can even plug in interesting irrational numbers, like x could be the square root of 5. And the corresponding y value, if we plug in the square root of 5 for x, 2 times the, oops, I need a comma, 2 times the square root of 5, I don't need to slash that, that's something else, minus 3 is a point on the line. So there's another pair of points, an x value and a y value, that satisfy the equation y equals 2x minus 3. So just to reiterate, a line is a collection or a set, infinite set of all the points that make this equation true. 1, -1, 2, +1, 3, 3, and so on and so on and so on. You can click on here and see, right, lots and lots and lots of points that satisfy that equation. Okay, let me stop sharing there. Let me reshare my other screen. Oops, let me share. Sorry, I'm really good at this. Okay, so that's the idea. When you're plugging in a point, you're just saying, oh, if I plug in this x value, do I get the y value I'm supposed to get? So I could also ask the question, like, you can also get this better in focus. There we go. What page am I on? Page 6. Is the point 2, -5 on the line y equals 4x minus 7? Let's find out. If I plug in x equals 2, then I get y equals 4 times 2 minus 7. So y equals 8 minus 7, so y equals 1. So no, 2, -5 isn't on the line. So when I plug in 2 for x, I should get y equal to 1. So the answer is no, but 2, 1 is. Just to kind of ask the question the other way, what about the point 3, 5? Well, let's try. So I plug in x equal to 3. I get y equal to 4 times 3 minus 7. Y equals 12 minus 7. Y equals 5. So that's a big yes. 3, 5 is on the line. The reason I'm kind of mentioning this is because this is the process that I'm kind of using to, one, check if an equation of a line is correct, that's supposed to go through a point, and two, to kind of, this is also what we're kind of doing when we're trying to find the b value to find the equation of a line. Let's do a couple examples of that, and then that'll be pretty much it. Oh, actually, one more tiny thing before we do that. So today we talked, or we did problems about parallel and perpendicular lines. I just want to point out something I might not have said as explicitly as I wanted to. Parallel lines have the same slope. Have to have the same slope. So if I said, find the equation of a line parallel to y equals -4x plus 7, passing through the point, I don't know, -3, 1. This line is telling me it has a slope of -4, which means my parallel line also has to have a slope of -4 because their slopes have to be equal. So my line has a slope of -4. But this y-intercept is garbage. Not garbage, but like it does nothing to do with this, right? This line, this new line I haven't found yet is parallel to that line, but the y-intercept here doesn't mean anything to me. I just know the slope is -4. So I want to find the equation of my line. I'm going to say, well, great. My line has the point -3, 1. And I can do this one of two ways. I can either say, well, y equals mx plus b. That's the equation I'm looking for. And I know what the m is. I know that my m is -4. So really I have y equals -4x plus b. But also this point has to satisfy the equation of the line I'm looking for. So when I plug in this point, the equation should be true, which means I can solve for b. So I'm going to plug in. I'm going to let y equal 1 and x equal -3. So when I do that, my equation becomes, instead of y, I get -3. And I get, y was 1. Apologies. Oof. Instead of y, I get +1. And instead of -4 times x, I get -4 times -3 plus b. So 1 equals 12 plus b. And then I subtract 12 from both sides. 1 minus 12 is -11. 12 minus 12 is 0. So I get 0 plus b, which is b. So b equals -11. We're not done. We have to go back and say, great, I almost had the whole equation. Now I'm going to plop in the actual b value here and say, oh, my equation is really y equal to -4x minus 11 or plus -11. You could also do this the point slope way. Point slope, where you would say, instead of doing it this way, you'd say y minus the y coordinate equals your slope times x minus the x coordinate. So then we have y minus 1 equals -4 times x plus 3. Y minus 1 equals -4x minus 12. And add 1 to both sides. I should say I was distributing here. Now I'm adding 1 to both sides. And -1 plus 1 is 0. And -12 plus 1 is -11. Same equation. Let's do one more, but with perpendicular. So let's say I'm given the line. Oh, this is page 8. So given the line y equal to, let's make it interesting. Sure, -3/7 x plus 2. Find the equation of the line perpendicular, I almost wrote parallel, to it. Sorry, it's not the best, it's not an English class, it's a math class. Find the equation of the equation line perpendicular that passes through the point. I'm not going to write the point. 5, -4. Sure, we'll make it gross. Why not? Okay, so the whole idea is that the original line, the slope, original line, the slope is -3/7. So the line we're trying to find the equation of, the desired line, the slope has to be perpendicular. I should say the line has to be perpendicular, which means the slope is the opposite inverse. So it's going to be, instead of being negative, it's positive, right? You always change signs. And instead of being 3/7, it's going to be 7/3. This is the way I like to think of it when I'm trying to find it. If I'm trying to check that these are perpendicular slopes, I would say -3/7 times +7/3 is -21/21, which is -1. But when you're just trying to find the slope of the perpendicular line, you're just going to take your original slope and flip it and change the sign. So then we're looking for, well, slope-intercept way, y equal to 7/3 x plus b. And then I'm going to plug in the xy coordinate of 5, -4. So I do that, -4 for y, and +5 for x. The numbers are going to get kind of gross. Sometimes that happens. So I have -4 equal to 7 times 5 over 1. 7 times 5 is 35. 3 times 1 is 3. There's nothing to do except leave it like that, plus b. And then I'm going to subtract that from both sides to solve for b. So -4 minus 35 thirds equals 0 plus b, which is just b. That is a 4, believe it or not. You need a common denominator over here. This was -4 over 1. I'm going to multiply it by 3 over 3 to get -12 over 3 minus 35 over 3. And finally, -12 minus 35. What I'm doing is I'm doing 12 plus 35, which is 47, and then saying -12 minus 35 is -47. So that's going to be b equal to -47 thirds, which does not reduce. So then my equation is going to be, instead of y equals 7 thirds x plus b, it's going to be y equals 7 thirds x plus -47 thirds, which I should just write as -47 over 3. Or just to be complete, we could do it the other way. We could have said y minus the y coordinate, which is -4, equals the slope, which is 7 thirds, times x minus the x coordinate, which is 5. This becomes y plus 4. We distribute 7 thirds times x is just 7 thirds x. And 7 thirds times 5 over 1. Well, 7 times 5 is 35, and it's minus 35, and 3 times 1 is 3. Then we add 35 thirds. Oh, no, we don't. We subtract 4 for both sides. We're trying to bring everything to isolate y. So y is going to equal 7 thirds x minus 35 thirds minus 4. Rewrite that as y equals 7 thirds x minus 35 thirds minus 4 over 1 times 3 over 3 is 12 over 3. And then just like last time, -35 thirds minus 12 thirds is -47 thirds. So whichever way you slice it, you should get the same answer, whether you like doing it this slope intercept way, where you start with y equals mx plus b and you plug in your point to find b, or you like doing it this point slope way, where you do y minus your y coordinate equals your slope times x minus your x coordinate. Both ways are perfectly fine. The last thing I'll say, well, in this video, not ever, obviously, just keep on talking. The last thing I just want to say is, as far as having some kind of intuition about how lines work, if your slope is positive, so if your slope is greater than 0, then the line should be going up from left to right, because you're having a positive run and a positive rise, right? Like, here's my run, which is getting bigger. Here's my rise, which is also getting bigger. On the other hand, if your slope is negative, so less than 0, then the graph is going to be going down from left to right. Because if you think about going from this point to this point, well, I'm increasing my x value, so my run is positive, but I'm decreasing my y value. Yes, you can think of it the opposite way. I don't like to. I like to think of my rise being negative because I'm going down, and my run still being positive. Here, my rise is positive, my run is positive. The reason I like to think of it this way is because usually when you're thinking about how graphs work, we usually go from left to right. So I'm going from left to right, my run, my change in x is always positive. So if I'm going this way, well, now my rise is positive because I'm going up as I go from left to right. Here, my rise is negative because I'm going down, so I'm going from left to right. And that's really that's just so you have some intuition about like, oh yeah, if I have a positive slope, I should be expecting my line to look more like this, or maybe steeper, or maybe less steep, but still having a positive slope. On the other hand, if my slope is negative, I expect my graph to be going down from left to right. Maybe it's really steep, I have like a -4, or maybe it's really shallow, like a -1/2. But either way, these slopes all on this side are positive because they're going up from left to right. These slopes are all negative because we can see the graph is going down from left to right. I think that's all I wanted to cover. Let me just double check my own personal notes here. I think that was it. Yeah. So tomorrow in class, I'll have a handout as usual, and we'll just have some Pythagorean theorem questions on it, really just kind of finding probably the unknown side of a right triangle. And then there'll be some more line review just to get more practice with lines, because I think, I know we kind of hit lines kind of hard, but you see a lot of lines in calculus, so it's good to be very comfortable knowing what they look like and how to just throw them on a graph without too much effort. All right, it's been a good first week. I will see you all tomorrow. Well, see you all tomorrow in class, and I'll also see you all tomorrow in after class at 3 o'clock for, I forget what it's called, for some problem solving and UUE, which I honestly don't remember what UUE stands for, but I'll be there, and Grant will be there too. So we've got some fun, I think fun math problems lined up that are less mathy and more like logic-y kind of problems, and I think they're pretty interesting. One of them has to do very tangentially with my birthday, not really. But yeah, I'll see you all tomorrow. Bye.